So remember what was our original purpose? The original purpose was to try and extend things like length, angles, and projections into spaces where these are not defined naturally because they're not geometrical spaces. So can we do that? Yes, we can. Now we have an inner product, we can define these ideas. For instance, the usual length. How did we define length? Well, we defined the length of a vector, both low or high dimensional Euclidean vector, as the square root of u dot u. Well, all we have to do is actually define the length as the square root of the inner product of u and u. And notice that this is a good definition, a proper definition, because of that positive definite axiom. We can be sure through that positive definite axiom that the quantity under the square root is always going to be positive. Okay. What about angles? Well, for Euclidean vectors, we defined the angle theta, or we proved in low dimension that the angle theta was given by this particular formula. Well, this is all we have to do is change the dot product to the inner product and use the same length that we have just defined up above. So all we need is to change the formula to this one. And now we have defined the angle between any two vectors in the vector space, even though those vectors may not have any geometric aspect whatsoever. You may wonder what's the use of defining these things in vector spaces whose objects are not geometrical objects. Well, it turns out that again what we can do is extend a lot of the properties that people have found in geometry to other things with applications. We're going to see one such application in the last segment of this class, but there is way more that we can do. So finally, how about projections? Well, same idea. Remember, this is the projection formula. Well, is there anything that we cannot change to inner product structure? Of course not. There is u dot v. All we need to do is change that to u inner product with v. And norm, or the length in the bottom, well, it's the same one as the formula we have up there. And so therefore we can find projections from one vector into another, even though they're not geometric projections. Again, both in class and in one of the seminars, you're going to see what interpretation this may have for objects which are not geometrical objects. So, more generally speaking, once we have an inner product, all these geometric concepts come alive, they can be used, and in fact they do have applications, although we may need to develop first a little bit of a better understanding and familiarity with the concept before we can go to some of these applications. But let's have a look at one of these applications. Let's see what happens. We're going to meet an old friend, and maybe if you have heard me say this before, you may remember, you may already have figured out what I'm talking about. But let's see. Let's say that we are in a vector space with an inner product, and u and v are orthogonal. Well, what does that mean? Well, what did it mean for regular Euclidean vectors? We know that two vectors are orthogonal if their dot product is 0, right? Well, we don't have a dot product now, we have an inner product. So we're going to say that two vectors are orthogonal if their inner product is 0. Okay? So let's assume that that is the situation. And now, let's have a look at this thing. Probably you have figured out where we're going with this. So let's compute the square of the length of the vector u plus v. And what we're going to do is we're going to do that by using just those 4 axioms, by going through the 4 axioms and the definition, of course, of what we mean by the length of a vector. And so this will give you also a little bit of an opportunity to see those axioms in action. So first of all, by the definition of the length length squared of u plus v is simply going to be the inner product of u plus v and u plus v itself. And we know this is going to be a positive number because of the positive definite nature of the product. Okay. Now, let's have a look at the first vector in there. It's a sum. Okay, so what we can do is we can use the distributivity property axiom of the inner product to split that into the inner product of u and u plus v, and plus the inner product of v and u plus v. So we've used the distributivity property. All right, now focus on this on both of these vectors, and remember that we have a commutativity axiom. So what we can do is we can actually flip the order in which the two vectors are placed in each of those two inner products. So what we're going to do is we're going to rewrite again those two, but in the reverse order. Okay, so now we have again a sum as the left vector in the product, and we can again use the distributivity property or the distributivity axiom of the inner product to split both the left and the right hand side products into two pieces. So we're going to use those sums, distribute each of them into use those sums to distribute each of those products into two pieces, and so we have u times u plus v times u, and then for the second product we have u times v and v times v. But now notice that again, because of the commutativity axiom, we can write vu as in fact uv. And now what do we have? Well, the first product here is just u times u. The second one is u times v. But remember, by our assumption, that's 0. And so is the next product. And the last one is going to be v times v. All right. So what we're left with is just u product with u plus v product with v. But how much is u product with u? Well, that's just the length of u, isn't it? Squared, of course. And v product v is going to be the length of v squared. And so we're going to write it like, we can write that like this. But now notice what we have found out. That if u and v are orthogonal, the square of the sum, the square of the hypotenuse, is equal to the sum of the squares of the two sides, or the two vectors, right? So here again we find the Pythagorean theorem, and this time is for general vectors, which means vectors which may have absolutely nothing geometrical. Again, we're going to see that in class, in the seminar, and you may not be able to see many more applications of this in this course, but again, there are applications, and hopefully you're going to see them in the future, and once you see them, you recognize them as being the fruit and the consequence of this idea of inner products.